Hey, Ronald. Actually, did I upload?
Hello.
Hey, how's it going?
Hi, Professor.
Hey.
I got both my codes running for finite volume and finite difference,
Okay,
but
great.
my videos don't look. They look similar, but not quite the same as yours.
Okay.
You think I
Um.
could see you during office hours?
Yeah. I have office hours tomorrow, and so we can take a look at the code then. If you want to send me your code so I can take a look beforehand, then I can do that too. Yep.
Sure. I'll be sending you both.
Okay, sounds good.
Thanks.
All right, it's 5:30, so let's go ahead and get started today. All right, and so for the last time this semester, good evening, everyone. How's everyone doing today? Good, good. Yeah, it's our last class session together. I'm good. I'm good. You know, think feeling probably the same as everyone else, just tired and kind of overwhelmed, but you know, almost at the end. And so summer break is right around the corner. Just have to get over one last hump, and then we'll be there. So yeah. Okay. And so today, you know, is going to be another chill day, and so there's nothing in this class or the last one which is going to show up on the final project or in any way. But this is just for you guys if you're interested in running OpenFOAM. Okay. And so I will say that I spent the last couple of days exploring OpenFOAM a lot, and I will say that even though we're going to be spending about a week and a half on this, we are barely scratching the surface. And so, and like I use that term a lot for a lot of stuff, but for OpenFOAM, really, that goes really, really deep from here. And so, I think, if you want to use OpenFOAM for any kind of work that you're doing, what we're doing in this class is really, really just the very, very beginning. And so, I would take this, if you're interested in using OpenFOAM more, I would take, what we learned in this class and, and apply it to, reading their official documentation and reading some of their example codes that they have online. And so, I think what we're doing here is enough just to kind of give you the general idea, especially today, the general idea of how to set up simulations in OpenFOAM. But to really get into the details and to really set something up on your own, you're gonna have to do a lot of other reading, right? My goal today was to, kind of show you what things that, first of all, what are the things that you need to set, where you need to set them, and then how you set up like your file structures and run the code. Because none of that stuff is trivial. So everything I think will be kind of a new thing for people. Okay. And what you'll hopefully see is that a lot of the steps that we're going to do, they mimic very closely to a lot of the setup that we've done in throughout the rest of this class. And so doing things like applying the mesh, setting time stepping values, applying the size of the domain, parameters, all that stuff. And so, a lot of what we cover today can be extracted from, kind of how we just set up our jobs in general. And so, I'm hoping that a lot of this will be kind of somewhat familiar. I think it's just the format and the syntax of doing so. I think that probably will be the steepest learning curve. Okay. All right. And so before we begin, I just want to just remind you guys to fill out the SOQs. Okay. And so SOQs, I don't remember. I think we talked about them on Monday. But SOQs are a really important part of how we develop our curriculum. Okay. And so typically the way that things work is that things evolve in the professional engineering space and new tools come out faster than we can adapt here in the classroom. And so we really rely on you guys to give us feedback on first, just first and foremost, how the class experience was. And so whether, tell us all the good things, all the bad things that was part of this class, but also just like, what are you hearing about, about like computational heat transfer out there, and what are some tools that you want to learn, right? And so, this whole tutorial here with OpenFOAM, this was born from feedback from previous classes that people said, they're interested in learning this stuff, and because they want to apply it to their own projects. And so, this was something that I added to the class just this year because of feedback that I got from you guys. And so, I know it might seem like a lot of times you do those evaluations and you write those comments and it kind of seems like it goes to a black hole. But we do read those, and I say that I at least I can say that I read all your comments and I read, all the feedback that you give really carefully, and I try to incorporate that into my future classes. So, one thing I always tell my students is that, when you're filling out those SOQs, just be honest. That's always the main thing. So it doesn't matter if your honest opinion is, if it's good or, if it's bad, I honestly want to hear how this class went for you guys, and honestly what you think, can be improved, because that's how we all improve, right? So we get honest feedback from people that we respect, people that that are going to be affected by it, and we incorporate them, right? And so, when you fill out those SOQs, if you haven't done so already, just be honest. That's the main thing I want to say. Okay. All right. So any other questions on anything before we get rolling for today? Okay. All right, and so today we're going to be running through the last tutorial that I have for OpenFOAM. And so this is something I just posted this today because I finished typing it up yesterday, but I realized I forgot to post it. And so if you go to week 16 on our Canvas site, you should see there's a new link down here for setting up and running simulations in OpenFOAM. Okay. Right, and so we're basically going to be running through this PDF today on how to set up these simulations, right? And so the example case that we're going to be running with today is something that probably is going to look familiar to you guys, okay? Because it's we're working with a square domain, and so that's something that we've basically been working with all the time here in this class, just due to its simplicity. But we're going to be working with the fluid mechanics situation, okay? And so this particular situation here, this setup and these boundary conditions, is for a very specific case called a lid-driven cavity flow, right? And so this is a very classical kind of first, it's like baby's first CFD problem. And so this is kind of the very first thing that people set up, and this is what they use to test their code, right? And so the situation is very simple. And so you have a cavity, right? And so all these gray walls right here, you can kind of think of them as solid walls, okay? And so you can think of this almost like fluid in a box. And so it's kind of trapped in a box. And so no fluid can escape. And so what we're gonna do is that on the top of this cavity where we have this lid, we're going to assume that we're going to basically take the lid and slide it across the top of the cavity, okay? And we're going to be continuously doing this, and so that you can imagine that there's kind of a conveyor belt on the top that's going to be constantly going forward, okay? And what that's going to do is it's going to apply a velocity of 1 meters per second going to the right on the top, okay? And then by doing that, because this container is closed, that's going to drive flow to the right, and it's going to bounce off this wall, and it's going to bounce off this bottom wall and bounce up here, and you're going to end up with kind of this swirling pattern like this, where the flow kind of goes in a circle, okay? Where the colors here indicate velocity magnitudes, and so where you see areas that are like red or orange, that's usually the faster velocities, and then things that are like purple and blue, those are much slower, okay? And so you have much faster flow near the top of the cavity, and then much slower flows near the bottom, because this is kind of far away from the moving boundary. Okay, right. And so today we're gonna go over how to set up this kind of simulation in OpenFOAM, how to prepare all the files for it, and then how to view the results afterwards. Okay. And so luckily, this case is not that expensive, and so it's roughly about the same cost as all MATLAB codes, and so it's not going to take very long to run. And so we're going to focus mostly on what files you need to set up, what parameters do you need to set in order to run this job. Okay. All right. So any questions on just the setup or the what we're going to do today? Okay. All right, and so let's go ahead and if you're going to be following along, you should go ahead and open up your Ubuntu terminal. Okay. Right. And so first thing we need to do is we need to copy the simulation files over. Okay. And so just like the PITS daily case that we did on Monday, this cavity flow is actually already fully worked out. Okay. And so all we're going to do is we're going to go basically through all the input files one by one, talk about what each one accomplishes, and how you would actually set this up on your own. Okay, so actually let me first delete my cavity flow here. Okay. All right, and so the first thing we're going to do is, if you're opening up your Ubuntu terminal, is to go into a folder where you have everything else organized. Okay, and so I think in the last class I told you to make a new folder, right? And so remember our Linux command for making a folder is mkdir. Okay. And I told you to make a folder where you can store all of your OpenFOAM tests, okay? And the reason we do this, remember, is to kind of keep all of our files organized so that we don't really lose anything, okay? And so for my case, I already have a folder for this, and so the folder is called OpenFOAM, and so I'm just going to go in here, okay? And then from here, I'm going to copy the files over, right? And so the files are already on your system. The only thing is we have to copy them to this location because it's a lot more convenient, okay? All right, and so the command we're going to run is we're going to use a CP command, okay? And you're seeing here that I'm running the CP command with a -r flag, okay? And so what that does is that it basically says we're going to copy an entire folder. Okay. Right. And then we're going to copy this entire path just like this. Okay. And so you're going to cp-r, and then you're going to do a $foam_tutorials, all in caps, /incompressible/icofoam/cavity/cavity. Okay. And this last part here is really important. And so it looks really small here, but you have to end this statement with a space period. Okay. And so what that's going to do is that it's going to copy all of those files, all this entire folder, into this current location. Okay. All right. And so I'm going to hit enter. And if you don't see the system complain, then you've done the right thing. Okay. And then after I hit an ls command, you can see that I've now copied this folder called cavity. Okay. All right, and so let's go inside this cavity folder. And so let's go ahead and cd cavity. Okay. And now we're inside the cavity folder where you can see we have these 3 other folders here. Okay. And so you can see we have one folder called 0. Okay. We have another folder called constant. And we have another folder called system. Okay. All right. And so the way we're going to set this up is we're going to go into each of these folders. Inside each of these folders, they're going to have some text files. Okay. And then from those text files, we'll see, how we actually modify them and how we set them up in order to run our simulation. Okay. All right. And so the first thing we're going to do is we're going to talk about how do we specify our domain and how do we actually mesh it. Okay. So actually, let me go ahead and bring up a previous MATLAB activity, and I'll kind of show you kind of the parallel to everything else that we've been doing in this class. Okay, so let's do unsteady convection diffusion FV. Okay. All right. And so if we open up kind of one of our old MATLAB codes, you can see that the first thing that we do here is we define the variables for the problem, right? And so we set things like we set the length of the domain, we set the number of cells that we want in each direction, right? And so in this case, we have a 30 by 30. Okay. We compute the number of cells, we compute the grid spacing. Okay. And from there, we're able to determine our mesh, right? In other words, we're able to determine our computational domain, right? And so just like that, in OpenFOAM, that's usually the first thing that you're going to do. And so we need to define our domain, right? Okay. And so our domain looks like this. And so, just like we've always been working with, our domain here for our lid-driven cavity flow will just be a box, right? And so what's unique about this box is that, you can see it's in 3 dimensions, right? And so it's not usually our 2D square that we usually work with, but we actually have a 3D box, okay? And the reason for this is that OpenFOAM, for all of its complexity, it doesn't have a legitimate 2D solver, right? And so it can't actually solve true 2D problems inside OpenFOAM. And actually, the reason for that is, I think you guys will understand too, is that if you compare your code for a 1D problem versus a 2D problem, some of the principles are still applicable, but you can see that they look like very different codes because the formulation in 1D looks very different from the formulation in 2D. Okay, and so OpenFOAM said that because we'd have to basically write a whole new code for a 2D problem, let's not do that. So let's just write a 3D code. But then we'll make some modifications for people who want to run 2D simulations, okay? But just keep in mind that we're working with a 3-dimensional geometry here. It's just that we're going to treat it like it's 2D, okay? And then for this particular problem, we're going to mesh it with 20 cells in the X direction and 20 cells in the Y direction, okay? And so our NX is going to be 20, our NY is going to be 20, okay? Right? And so the file that we want to view here, the file that we want to edit to see how we modify our domain is this file called block mesh dict. Okay. All right. And so just like in the tutorial here, that file is located in the system folder. And so first thing we're going to do is we're going to cd into system. Okay. Right. And so after we cd into system, we can see here that we have four text files. And so we can have one file. We have one file called block mesh dict. We have another file called control dict, another file called fv schemes, and finally another file called fv solution. Okay. But for now, we're going to focus on block mesh dict. Okay. Actually, let me see if this works, because my gedit actually stopped working on me. Okay, it's still broken. Okay, never mind. All right, so we're gonna look at this in Vim. Okay. And so if your gedit is working, you can open it there, but basically you just need some kind of text editor to open up this file. Okay. And in this file, it's going to look like we have code here, and we're going to use this code to define our domain, and we're going to use it to define our mesh. Okay. All right. And so when you open this file, first thing that you should see are things that are up here. Okay. And so all of these lines here appear in blue because all of these are comment lines. Okay. As you can see here, that for this situation, it's using a C++ form of commenting. And so in C++, the way that we start a comment is we use a slash and a star. Okay, so you can see that in the very top right. And then we end the comment with a slash and a star as well. Okay, let me widen this a little bit. Okay, and so you can see here we have a big comment section up here. And so this, just like in MATLAB, comment sections aren't read by the code. And they're just there to provide some information to the readers. Okay, and so for in this case, OpenFOAM, they put an ASCII version of their logo, which is kind of nice, I guess, right? As well as putting like the version number and the website. Okay, and so this part up here is optional, and so you don't have to put this for your own files, but it's kind of nice because then it shows you that this file it belongs to like an OpenFOAM kind of ecosystem. All right, and so the next thing that you'll see here is just some more header information. And so you'll see that this section of code right here, called starting with foam file and ending with this bracket here, this one is not highlighted blue, and so this is not a comment line. Okay, and so what this is just a line of code that denotes basically the version number for this OpenFOAM file, as well as some other information. Okay. And so if you're setting this up on your own, you can just copy and paste this. You can just copy and paste this entire section right here, and copy that into any of your other OpenFOAM files. Okay, because more than likely, this stuff shouldn't change all that much. Right? Okay. And so for this top section here, you don't really have to worry about anything. And in fact, one way that you can tell is that we have this kind of another big comment line right here. And this tells you that, above this line, you don't have to worry about stuff. But below this line, this is when you need to start, implementing things. Okay. Okay. And so the first command that we see here is a command called convert to meters. Okay. And so typically the file format that you'll see in these files, that you'll always start with some kind of command name. Okay. And so that's always going to be written out in just plain text. Okay. And so in this case, the command name is called convert to meters. Okay. And then after that, you're going to have a number or a list of numbers that's going to be, what you're going to set for that setting. Okay. All right. And so in this case, we're running a command called convert to meters. Okay. And then the argument that we're going to pass to this is 0.1. Right. And so this is kind of a, for a lot of, for a lot of jobs, I don't think I would have this. And so all that basically does is to say that, whatever coordinates that we have here, we're going to multiply that by 0.1, basically all the coordinates by 0.1, and then that's going to be our kind of like true coordinates. Okay, because if you look at the original geometry here for this problem, we can see here that the lengths of the square are 0.1 meters. Okay. But I guess, the author of this example problem thought it'd be too annoying to write 0.1 all the time. And so they want to do things in terms of nice whole one numbers. Okay. And so in order to make it into a system that has the same units as this, all they did was let's just say, let's just multiply everything by 0.1. Okay. It's a little bit strange, but, it's, that's just kind of how they do it. All right, and so the next command that you see in this text file is something called vertices, right? And so what this does is that this will define all the endpoints or all the vertexes for our geometry. Okay, and so I want you to notice something, because if I scroll down here to the geometry, you can see here that all of the nodes and all the vertexes here are numbered, right? And so starting with node number 0 here at the bottom left, then it goes to node number 1 here on the bottom right. and node 0 is at the origin, okay? And we have node number 2, node number 3, okay? And then it resets and goes down to 4, 5, 6, and 7, right? All right, and so if I pull up the script again, right? Let's look at the order of these coordinates here and correspond them with the order of the vertices here, okay? And so the first thing that we have is a coordinate for the origin, okay? So that's gonna be 0, 0, 0, okay? And if we look in to see, you know, which vertex that corresponds to in the main figure, we can see that corresponds to point number 0, which is at the origin, okay? And so what you'll see here is that, you know, each entry here, you know, each of them separated by an enter sign, each of those are going to be, you know, a separate vertex here on our cube, or on our box, I should say, okay? And so index 1 is going to be at the coordinates 1, 0, 0, okay? And that's true because you can see that, you know, we have the x direction going horizontally here, okay? Vertex number 2 is going to be at the location 1, 1, 0, okay? And so the same thing. So if we go over 1 and up 1, while keeping the z coordinate the same, and so that's going to give us point number 2. And then point number 3 here is directly above the origin, and so its x value is 0, and then its y value is 1. Okay. All right, and then you can follow the same kind of logic for all the other locations too, right? So starting from 4, you go, you're kind of at the same level of the origin, but you go 0.1 in the direction this way, okay? And then kind of all the same thing over there. Okay, and so as we kind of go through the rest of this file, I want you to kind of remember and keep these node numbers in mind, because we're going to reference them whenever we apply like boundary conditions, or to name walls, or to apply our mesh. Okay. All right, and so any questions on this so far? Oh, excuse me. Need more sleep. Okay, and so that's going to go ahead and define our domain. Okay, and so if you compare that to our MATLAB scripts, you know, this is kind of the first part of the script right here. Okay, and so here, you know, we've already kind of established that we're working with the square domain, and then Lx and Ly determine the length in those directions. Okay. And so here we're kind of defining the same thing, but we're kind of being a little bit more explicit with our geometry, okay? And so we're strictly defining all of the vertexes or all of the nodes that are associated with our full geometry here, okay? All right, and so the next thing that we're gonna do is we're going to mesh our geometry, okay? And so these next lines of code here are going to define that mesh, right? All right, and so the way that you define your mesh is that you make a new block called blocks, right? And so what this says is that, you know, we're going to break up our domain into blocks and then mesh them according to these settings, right? All right, and so for this one, we just want a very simple mesh because we just have kind of one region in our domain, right? And so the first thing we're going to do is we're going to start out with a command called hex, right? And so what the hex means is that, you know, we're going to use what's called hexahedral elements, okay? And so hexahedral elements are basically just like a box, right? And so hexahedral is kind of the fancy name for a box. And so since we have a box geometry here, we're going to mesh it with a bunch of boxes, right? Okay. And so the next thing that we have to define here is we have to define our the vertices that go around our domain where we want to mesh, okay? And so in this case, you know, we just have one region. And so we're just going to define a region by 0, 1, 2, 3, 4, 5, 6, 7, okay? And so that defines all these vertices here, okay? And so the way that you can follow this is go 0, 1, 2, 3, 4, 5, 6, 7, okay? And so because those vertices kind of form a closed space, you're going to be able to mesh it from there, okay? Okay, and so the next thing that we're going to need to put in here is the mesh density, okay? Or in other words, how many elements that we want to have in each direction, right? And so in this case, since we want 20 cells in the x direction, 20 cells in the y direction, we're going to fill this in with 20, 20, and then 1. Okay. And so the 1 is to denote the fact that, you know, yes, we have a 3D domain here, but, you know, we don't really care about what happens in that side. And so we're just applying just one cell depth in that direction. Okay. All right, and so the last thing that we have here is a command called simple gradient and simple grading. Okay, and so don't worry about that for this because it's not relevant. But this is just another way that you can modify your mesh, or in other words, how your mesh is going to change as you move in a certain direction. Okay. All right, and so just to summarize, when you define your domain, you have to apply this setting here called blocks. And then inside the blocks, you define the part of the geometry that you're going to run the mesh on, and then you apply the actual meshing settings for that. Okay, and so in this case, the meshing settings are 20 by 20 by 1. Right. Okay, and so any questions on this? Okay. All right, and so that's our domain in our mesh. Okay. And so the next thing that we have to do here is we have to name our surfaces, okay? Right, and so this is really important because we're actually not going to apply the boundary conditions in this file, because this file, the only thing that it's really concerned about is just the domain as well as the mesh, okay? But what we do need to do is we need to define kind of the regions where we want to apply those boundary conditions, right? And so in our MATLAB codes, we kind of took this for granted because when the way we applied boundary condition is we use values of I and j, and then loop them over our system. But for this case, we have to be a little bit more explicit about how we name our surfaces. Okay. And so what we're going to do here is we're going to create what's called named surfaces. Okay. And so it's surfaces that we're going to define with these indices that we can refer to later in the code. All right, and so the first one that I want to talk about here is the moving wall, okay? And so the moving wall, of course, refers to the lid of our cavity, right? And so since we're going to apply a velocity boundary condition here, we need to specify this surface in our model, okay? And so the way that you do that is you take all of the vertices here on the surface and you just list them kind of one after the other one, okay? And so in this case, our surface is defined by the vertices 3, 7, 6, and 2. Okay? And so if you trace a line around all of those vertices, you get our surface. Okay? And the ordering is important here. And so when you select the order for for the nodes that you put in for the boundary conditions, they have to kind of form a path that kind of makes sense. Okay. And so the reason here we chose 3 to 7 to 6 to 2, right? The reason we did that is because that kind of traces a nice a nice outline around the outside of the surface we want to apply our boundary condition. Okay. The lower brackets look like sad faces. Yes, it kind of does. Yep. All right, and so that's the moving wall, and so we just have one moving wall, and so we just have to define one of these. Okay. And so the other things we have to define here are the fixed walls. Okay. And so remember, we have 3 fixed walls in this situation, and so it's going to be the left side, the right side, and the bottom surface. Okay. And so that's why we have 3 entries here under fixed wall. Okay? And so our first fixed wall, is going to be the this left side here. Okay. And so the way that we define that surface is we go from node 0 to node number 4 to node number 7 to node number 3. Okay. So you can see again we're tracing out this kind of rectangle-y shape, right? And so our second fixed wall is going to be on the right side, it looks like. And so it's going to be 2 to 6 to 5 to 1, right? And then our last fixed wall is going to be on the bottom. And so we have 1 to 0 to 4 to 5. Or I'm sorry, 1 to 5 to 4 to 0. Okay. And so again, you can see that we've made kind of a closed rectangle, and it has it's defined all by its vertices. Okay. Okay. And so that's it for this file, right? And so just to kind of summarize, and so if you're setting up your OpenFOAM simulations on your own, you have to make a file that looks like this, and it has to be called block mesh dict, right? And so because when you run OpenFOAM, it's going to explicitly look for this file, and if all the information is not in this file, then OpenFOAM won't be able to run your simulation. Okay. All right. So any questions on this? Okay, All right, and so now that we're done with this file, we can go ahead and exit. Okay, and so if you're using gedit, you can just click save and exit. But for me, since I'm using Vim, I have to do it the Vim way. Okay. Right. All right, and so to actually run the mesh, we have to run a program called block mesh. Okay. And so when you return to the terminal here, make sure you do cd ... because we want to return to the root folder for this simulation. Okay. And then from here, we're going to run the command to actually create the mesh. Okay. And so the command for actually creating the mesh is called block mesh, right? All one word, where the mesh, the M in mesh is capitalized. Okay. And so if you hit enter, you can see that the mesh is going to be generated. Okay. All right, and so there's a lot of information here on this page, but the only thing I want you to guys to kind of pay attention to is this, okay, which is the number of cells that you have in your domain, right? And so if we go back to the problem statement, we can see that we're applying a mesh with 20 cells in each direction, okay? And so what this tells us is that the amount of cells that we have overall for the entire domain is going to be 20 times 20, which is 400. Okay. Right. And so when you're running your mesh, this is always something good to check, just to make sure that you get a number of cells approximately equal to to what you expect. Okay. Because if this was not 400, then probably something went terribly wrong. Okay. And then we need to go back and check it. Right? Okay. Oh, excuse me. Sorry. Okay. And so from here, what we can do, so this isn't in the tutorial, but what you can do is you can check your mesh. Okay. All right. And so to check your mesh, we're going to run a program known as parafoam. Okay. And so this is the program that we ran last time in order to view our simulation results. Okay. But in this case, we're just going to use it just to view the, oops, shoot. Okay. In this case, we're going to use it just to view our mesh. Okay. What's going on here? Okay. Oh, I was just viewing at my thing. Okay. And so here we have our square domain. Okay. And so to view the mesh, what you can do is you can go over here to this section right here and click where it says surface. Okay. And then we want to change this command here to surface with edges. Okay. And so with that, we're going to be able to see the edges of our cells. Okay. And you can see here we have a very uniform mesh. Okay. And so if you count the number of cells in this direction and in this direction, you should get exactly 200 in each direction. Okay. All right, and so that's everything with the mesh. And so now at this point, our domain is loaded in, it's meshed, and now we're ready to apply boundary conditions. Okay. Oh, what did I close? Oops, I closed the PDF. Okay. All right, and so let's go ahead and set up boundary conditions. Okay. And so the boundary conditions are in a folder called 0. Okay. And so in here, we're going to go to folder 0. Okay. And so from the cavity folder, you can do cd 0. Okay. And then once I'm inside this this folder here, you can see I have two files. One is called U, and the other is called P. Okay. All right. And so what this basically tells you is that this will be our way to supply boundary conditions on U, which is the velocity. Okay. Or more specifically, it's the X, Y, and Z components of velocity, and so it's all three components. Okay. And also on P, which is the pressure. Okay. Because when you're solving Navier-Stokes, you're solving for both the velocities in the system as well as the pressures. Okay. So that's why we need to have two separate files here. So one for the velocities and one for the pressures. All right, and so both of these are text files. So let's go ahead and open up one in Vim. Okay, so I'm going to run vimp. Okay, and then by doing that, you can see here that we are inside this file here, which defines the boundary conditions. All right, and so the first thing you should see is that we have all this header information, and so all of this is exactly the same. Okay, And so in all of your OpenFOAM scripts, you can just copy and paste this thing right here. Okay. And it's not until we get later on in the code, this is where kind of, you know, things are actually set up. Okay. All right. And the first thing we're going to look at is this command called dimensions. Okay. And so what this allows you to do is it allows you to specify what dimensions do you want for this boundary condition. Okay. And what I mean by dimensions are basically, you know, what are the units. Okay. All right. And so the way to read this is a little bit strange. As you can see here, we have a list of numbers. And so we have 0, 2, -2, and then 0, 0, 0, 0. Okay. Right. And so the way to read this, let me go ahead and insert here. Oops. Sure, we didn't mix anything up. Okay. And so the way to read this here is, you know, the last four numbers I'm not going to worry about too much because, you know, we're not going to get into it for fluid simulation. But the way to read this is going from left to right is going to be the dimensions for mass. Next is going to be dimensions for length. And next is going to be dimensions for time. Okay. And I'll leave a ... there for all the other stuff. Okay. All right. And so what this says is that, you know, we're defining the units for this pressure in terms of length squared and then length and then time to the -2. Okay. All right. And so this is basically the units that we're using for the pressure term. Okay. All right. And so this might seem a little bit strange because, you know, usually when you think of pressure, you think of units like pascals, right? And so pascals is a newtons over meter squared. And so, you know, and I would say, you know, traditionally that's what you would use in for the pressure is, you know, something of that nature. But for this case, you know, because we're running a steady Navier-Stokes solution, what we can do is we can divide the pressure straight away by the density. And so that'll actually create something known as kinematic pressure. Okay. And so you can read more about that here. Okay. Right here, yes. And so in this paragraph on page 8, you can read more about the kinematic pressure and how we obtain it. Okay. But the upshot here is that it has units of meter squared over second squared. Okay. And so what we're telling OpenFOAM here is that, you know, the length parameter here, which is the meters, that's going to have an exponent of 2. Okay. And then the time parameter, which is in units of seconds, that's given in an exponent of -2. Okay. And so when you put these together, you get length squared over time squared. Okay. Okay. So any questions on the dimension command? Okay. All right. And so the next thing that we can specify here is we can specify any internal field. Okay. And so what the internal fields are going to do is this allows us to set any kind of like offset solution in our main solution. Okay. You know, so I will say that this is pretty rare, and so for most of the cases you don't really want to set this, or there's really usually not a good reason to. But for some reason, if you want to set like an offset pressure or an offset temperature in your Tarn solution, so you're just going to add everything by by a certain amount, you can use this field to do that. Okay. All right, and so those are the dimensions and the internal field, and now we actually get to the interesting part, which are the boundary conditions. Okay. All right, and so you can see here that the boundary conditions are started with a command called boundary field, okay? And then inside here, you can see here we have 3 different surfaces, okay? All right. And so if you recall from our previous file, you know, we had named all these surfaces here, right? And so we had created, you know, surfaces with these names defined by certain vertices, okay? And remember, this is so that we can apply different boundary conditions on them, okay? All right, so let's start with the moving wall first. And so with the moving wall, you know, we have our boundary condition of 1 meter per second for the velocity. But you know, it doesn't say anything about the pressure, right? And so for the pressure, you know, if you're not sure what the pressure boundary condition is going to be at a certain surface, one way that you can deal with it is you can just say, you know, just run the command called 0 gradient. Okay, and so you're going to have moving wall, and then inside the moving wall, you're going to have type, and then 0 gradient. And so same thing for the fixed walls. And so for the 3 fixed walls, we're going to apply a 0 gradient boundary condition, okay? And then for the front and back, we're using a special type of boundary condition called empty, okay? And so what the empty boundary condition does is that it lets ANSYS know that, even though that this solution here is in 3D, we only really care about the 2D solution, right? And so what this tells you is that the front of the box and the back, and so let me scroll down here, okay? And so the front of the box, which is defined by surface 4, 3, 6, 7, and the back of the box, which is 0, 1, 2, 3, okay? Those actually don't contribute to the results. And so, we can set this boundary condition to empty here, and that will, that will satisfy our equations. Okay, so for the pressure, not much interesting going on, because we're just, we're not really applying any pressure boundary conditions, and so we just kind of have all default settings here. Okay, so any questions on this? Okay. All right, and so that's everything with the pressure file. So let's go ahead and exit it. Okay, and now let's open up the velocity file. Right? And so this will be a little bit more interesting because we actually have a boundary condition that we're applying. Okay, and so first thing we need to do is we need to specify the dimensions for velocity, right? And so for velocity, we're running with units of meters per second, right? And so you can see here for the dimensions, we have a 1 on the length slot, and so that tells us we're going to have a length parameter of 1 up top. And then for the bottom, we have a time parameter of -1. Okay, and so this makes sense because our units for velocity are things like meters per second, things like miles per hour, right? It's always some kind of length divided by time, right? And so the way that we specify that here is through this. Okay, right. And so again, we have the option of adding an internal field. I don't really know why, but but that option is there for you. Okay. And then from here, we move on to the actual wall boundary conditions. And so these guys are actually interesting. Okay? And so let's start with the moving wall, right? And so the moving wall, remember, is going to be this wall on top of the box. Okay, and so that's going to be surface defined by 3, 7, 6, 2, right? If we go back to our problem schematics, this is the surface that's going to be moving at a speed of 1 meters per second. And so that's what this lines of code basically do. And so you say, for the moving wall, we're going to define a fixed value uniform velocity of 1, 0, 0. Okay, and then that's going to determine our moving boundary condition. Okay? Okay, and so for the other boundary conditions, they're more or less straightforward. And so the next one we have is fixed walls. Okay, and so for all the walls that are around this, we want them to be completely fixed with no slip. Okay. And so we can just say that, for these surfaces, apply a no slip boundary condition. Okay? And same thing for the front and the back. And so for the front and the back, we don't really have anything to put there. And so we're just going to put empty. Okay. Okay. And so any questions on this? Okay. Right. And so boundary conditions, it should be something that's very familiar to you guys because, we've been applying them for all of our MATLAB codes, as well as our hand calculations. Okay. And so we know that, boundary conditions are an essential part to any kind of computational heat transfer, computational fluids code. Okay. And so, that's what we're doing here with the, with these boundary conditions. Okay. And so as we're going through this, you'll probably notice me, I'm not really changing any of the files, right? And so the reason for that is, because this example was kind of already worked out by OpenFOAM. Okay. And so all I'm doing is basically just going over each of the input files and talk about what each of them do, so that, once you go and explore maybe OpenFOAM later on in your life, you'll know kind of what, kind of where everything is and kind of how to set things up. Okay. Okay. And so now that we're done with the boundary conditions, let's go ahead and exit from this. Okay. And the next thing that we have to set here are the physical properties. Okay. Okay. All right. And so our properties are going to be located in a file called transport properties. Okay. And so that file is located in the folder called constant. Okay. Okay. And so you can see here that, I moved out of the current folder of 0. I moved into the folder called constant. Okay. And then from here, I can see that I have a file called transport properties. Okay. All right. So just a quick Linux tip. And what you'll see, all the time is that whenever I change folders, what I do is I run an ls command right away just to see, what folders are in there. Okay. And so at this point, it's almost become kind of muscle memory for me. So, oops. And sometimes I do it more than once because I forget, okay? And so you can see here, as soon as I CD into a folder, I want to see what things are available to me. And so I hit LS right away, okay? Because then that'll tell you, which files you can open, which folders you can go into, because if not, you're kind of shooting in the dark, okay? Okay, and so now we're inside the constants folder. And so remember, the file that we want to open here is called transport properties. Okay, so let's go ahead and open that in a text editor. Okay. And so you can see here the our file that defines the properties for this simulation. Okay. And so in this case, we only have one property, okay? And so that property is going to be the kinematic viscosity. And so this kinematic viscosity is set to the value of what it has for, for water. Okay, right. And so again, you see this kind of bracket here with 7 entries. Okay, and so again, this is defining the units or the dimensions for viscosity. And so in this case, we're running with the viscosity of 0.01 meters squared per second. Okay, and so the way that we denote those dimensions here is using this vector. Okay. Oops, that shouldn't be there. Okay. Right, and so the kinematic viscosity has dimensions of meters squared over seconds, and so that's going to be length squared. Oh, actually, that should be length squared. Yeah. It should be length squared and then time minus 1, and so that's going to put the time variable on the denominator for this guy. Okay, and you can see here we're giving it a numerical value, which is 0.01. Okay, so any questions on this? Okay. All right, so let's go ahead and exit this. Okay. All right, and so the last thing that we need to set here are the time stepping properties. Okay. All right, and so let's go ahead and look at the file called control dict. Okay, if you remember from before, our control dict was inside this folder called system. Okay, and so we're going to CD into our system folder, and then we're going to open up the file called control dict. Okay, and so you can see here I'm using Vim, and I'm using our text editor, and we're modifying this file. Right? All right, and so as an analogy, if we look at kind of our usual MATLAB scripts, and this is speaking strictly of the unsteady simulations, right? Remember, one thing that we have to specify before we begin are the time step size, dt, as well as the number of time steps that we want to run, okay? And so OpenFOAM does it a little bit differently, but one thing you have to set for sure is the time step size, okay? And so the time step size in OpenFOAM is called delta t, okay? And so you can see here I have a time step size of 0.005, and so this is about 5 milliseconds for this simulation, okay? All right. And so from here, we have to, that takes care of the time step size. And so the next thing that we have to specify here is NT, which is the total number of time steps that we want to solve for in this simulation, okay? All right. And so here, what you'll see is that there's no explicit place where you can say, I want to run it for this many time steps, okay? But the way that OpenFOAM does this time stepping is that it defines things in terms of the start time as well as the end time, okay? And so the start time of 0, this tells us that, we're going to start our simulation when t is equal to 0, okay? And, we want to do this probably 99.9% of times, okay? Because it's just convenient, okay? And so you can see we do the same thing in our MATLAB script where we specify our time is equal to 0 initially, okay? And then the end time, this is going to be the last time that we want to simulate in our simulation, okay? And so in this case, we have an end time of 0.05, okay? And so the way that you compute the number of time steps is that you take the end time minus the start time, and then you divide it by the delta t, okay? Right? And so in this case, we have an end time of half a second, and our start time is 0. And so the number of time steps is going to be 0.5 divided by 0.005, okay? And that gives you a total number of 100 time steps, okay? Right, and so we're going to be simulating this for NT is equal to 100, which coincidentally is the same as this MATLAB script here, okay? Okay, and so any questions on this so far? Okay, all right. And so the last thing that we have to set in here is the right interval. Okay, and so the right interval tells us how often that we want to save our results. Okay. And so this is new, and so this is something that we haven't really dealt with in MATLAB, because in MATLAB I basically just have you guys save the result at every single time step. Okay, because for MATLAB, all we're producing is just a still picture, as well as a as well as a video sometimes. Okay, but for a large CFD code like this, for OpenFOAM, and you're dealing with kind of more practical problems, a lot of times you don't want to be saving results every single time step. Okay. Oops. Weird. Okay. And the reason you don't want to do this is because, if you imagine that, let's say that you're running a simulation on a mesh with like millions of elements, right? And so just to store the mesh, it's going to take up, maybe 50, 60 megabytes on your computer. Okay. And then you're going to run this simulation for, let's say, something like 5,000 time steps. Okay. And so if you save the results every single time step there, then what you're basically saying is that for every time step, you're going to save about 55 55 megabytes of data every single second, right? Or every single time step, right? And so if you run your simulation for 5,000 time steps, then the amount of memory that you take up is going to be 55 megabytes times 5,000 time steps. Okay. And so, let me pull out my handy dandy calculator. Okay. And so this is going to be, let's see, 275,000 megabytes. Okay. Or in other words, 275 gigabytes of data. Okay. Just for one simulation. Okay. And these aren't, these aren't kind of outlandish numbers, right? And so a lot of times you're going to have meshes that are really big, like 50, like in the megabytes. Okay. And if you run it for 5,000 time steps, and you save every single one, it's going to be a lot of data that you're solving for, right? And so, unless you unless you pay for like Dropbox Ultra Premium, or you have like a supercomputer, 275 gigabytes is usually way too much data just for one simulation. Okay. And so the way that we kind of combat this issue is that, we say that we don't want to save every single time step, because actually, a lot of times that's a little bit of overkill for viewing the results. Okay. And so in this case, what we're doing instead is we're saving the results every 20 time steps. Okay. And that's a little bit more reasonable, because then, we only save, 20, every 20 time steps. And so if we go back to our previous example, right? And so instead of saving for 275 gigabytes, if I divide this by 20, now you're only saving about 14 gigabytes worth of data, which is a lot more reasonable. Okay. Okay. Any questions on this? Okay. All right. And so that's the control. Okay. And actually, that's it. Okay. And so if we kind of go back to our MATLAB script here, and we think about all the things that we have to set before we actually run the code. We have to set our domain. We have to define our mesh. We have to set the number of time step properties. Okay. We define our physical properties, right? And so here we define it as the diffusion coefficient. But for fluids, the diffusion coefficient is the viscosity, and so we did that. Okay. And the other thing that we did was we defined, what boundary conditions that we want. Okay. Right. And so in here, our boundary conditions are kind of, implemented throughout. Okay. And so we're ready to go. And so we're ready to solve, right? And so we have everything, we've defined everything that we typically do in our MATLAB scripts, but we've done them in OpenFOAM now. Okay. And we've done it through a lot of confusing text files, right? All right, and so to run the simulation, it's actually very simple. And so you want to make sure that you're in this folder, okay? And so when you hit ls, you want to make sure that you see the folder 0, constant, and system, okay? And then the only thing you have to run here is called IcoFoam, okay? And so IcoFoam will call the solver for you, and then it'll run the simulation for you, okay? And so, once I hit enter here, it's going to start to run the simulation, and it's going to go really fast. And so just kind of, be prepared for that. Okay, and so I'm going to go ahead and hit enter, right? And so you can see here that it's running the simulation, and it's already done, okay? And so here our simulation only took 2 seconds because we're running with a 20 by 20 mesh, okay? But this easily could have been more, okay? If we had a more a more highly resolved mesh. Okay, and so the way that you find out if your simulation ended successfully is you basically look for these results, and you should see that the last time that gets printed should be kind of the last time that you put into your control date. Okay. All right, and so now let's go ahead and view our results. And so we're going to open ParaFoam. Okay, so let's go ahead and launch the program ParaFoam. Okay, and now we're back in. We're now back in here. Okay, but the difference now is that we actually have our simulation results. Okay. All right. And so first thing we're going to do is we're going to view our velocity field. Okay, because right now what you're seeing is just a block, and so this is just our initial conditions. Okay, and so if you want to view the velocities, you need to go to this section of ParaView right here, which is the view selector. Okay. And we're going to select velocities, okay? And some of you might be wondering, why are there 2 velocities here? So why is there a U with a dot, and why is there a U with a cube next to it, okay? And so these are velocities at different points in our mesh. Yep. And so the U with a dot next to it, that's going to be our velocities at the nodes of our mesh, okay? And then the U with a block next to it, that's going to be the velocities at the centers of our finite volume cells. Okay, and so it's subtle, and so you can almost think of this as like, the U with the dot as a, that's as if we solved it in terms of the finite difference. And so, remember in finite difference, our solutions are located at the nodes of our mesh. Okay, and then for the U with the block, that's as if we ran the simulation with finite volumes, and now our solution is in the middles of our cells. Okay, all right, and so there's slight differences, but they're mostly the same thing. Okay, and so the main difference here is that if you pick the U with a dot, you're able to see kind of the velocity here up top. Okay, so that's why you see kind of the top region of this domain lit up. Okay, and so that tells us that our top boundary here is being moved to the right. Okay, but then if you pick U with a cell, you don't see that because initially we have 0 velocity everywhere. So if I turn on the grid, okay, right, and so U with the cell is defining the velocities here at the center, okay, and so at this point, before the simulation has begun, this is essentially our initial conditions. Then we haven't, the fact that the velocity is up here hasn't propagated to the middles of the cells, okay, and so the middles of the cells don't know that the simulation has started yet. Okay, all right. And so how do we advance this in time? Because right now what we're viewing is we're only viewing the initial conditions, okay? And so if we want to view, the end result, all we have to do is to come up here onto this bar and then hit the play, okay? And so let me go ahead and turn this off, okay? Right, and so what you're seeing here is you're seeing the velocity field in our cell or in our domain at each of the different cells. Okay, and so you can see here it looks kind of pixelated. Right? It kind of looks like Minecraft, right? Because we have a pretty coarse mesh, right? And so because our mesh was only 20 by 20, our simulation here looks a little bit scuffed, right? If you want a smoother distribution, you can pick the U with the dot, and so that kind of smooths things out a little bit. Okay, and the reason for that is because with the dots, then ParaView, which is the name of this program, has some automatic rendering stuff that it kind of smooths those things out. But if you view things from the cells, it doesn't have that that feature. Okay. Okay. And so now that we've advanced this simulation to the end, what we're viewing here is the steady state solution. Okay. And so this is our velocity field. And so this is good. Okay. But usually we don't want to stop here. And so usually we want to, view a little bit more. Because all we're viewing here is we're viewing kind of the magnitudes of the velocity, right? But velocity is more than just a magnitude. So velocity is a vector. And so oftentimes we want to view, what direction the velocities are going. Okay. And so to do that, you can run a glyph command. Okay. And so if you go over here, there's actually a lot of different filters that you can run to view, like to interpret your results in a different way. Okay. And so actually, pair view is kind of another program that can take, that I can spend, a few weeks talking about, just because there's so many features packed into pair view, but we only have 15 minutes. So I'll just show you just kind of the cool stuff. Okay. All right, so let's look at glyphs. Okay. And so what glyphs are going to do is that it's going to put arrows in our domain that kind of show which direction the velocity vectors are going. Okay. All right, and so the way that we're going to use glyph is that we're going to go to these settings here on the bottom left. Okay. And then the main thing that we have to set here is the orientation array, right? And so the orientation array basically defines, or it basically tells PairView to say which field that we want to use to define which directions our arrows are going to go. Okay. And so you can see here there's only two options because we only have two vector fields. And so we can either pick U or we can pick U, right? So we can pick U with the dot or U with the cell. And so for this one, it doesn't really matter. Okay. Right. And so once we do that, we can go ahead and hit apply. Okay. And you can see here that now, from this, you can see which direction all the velocities are going. Okay. Actually, let me do this. Let me do it by cells. Okay. Right. And so if you do it by cells, and if you turn off the domain, right, then what you're viewing here is the velocity field, right? And so you can see here that we have kind of our swirling pattern, kind of like what we hypothesized, right? And so the top wall is moving forward, and then it's causing the flow to collide with the right wall, which then collides with the bottom wall, and then collides up here. Okay, and then all throughout, we end up with kind of the swirling kind of washing machine kind of flow field here. Okay, right. And so, so actually, if you're curious, last year's project actually looked very similar to this. And so I gave them a velocity field, that kind of swirled like this. And I asked them to kind of, solve the solution, about that. They didn't run CFD, but they ran a like a heat transfer simulation, with a swirling velocity field. Okay. So any questions on this? Okay. All right. And so that's technically, and so for our final, we have to do an OpenFOAM in MATLAB. No. So yeah, you don't have to worry about OpenFOAM for the final project. Just do the MATLAB implementation. But if you can run it in OpenFOAM, I think that would be really cool. But it's definitely not required for the project at all, because we've barely spent any time on OpenFOAM. No bonus points. Let's not do that. And so let's not add any additional pressure for people. And so yeah, so no bonus points. If you do it, I'll give you a handshake next time we meet, but no bonus points for the class. Okay, and so that's actually it for this tutorial. But we do have a bit more time. Smiley face sticker. Yeah, I can do that. I can give you a smiley face sticker. Right. And so we do have a bit more time, and so let me show you a couple other cool things in PairView, because PairView is actually a program that I'm very familiar with just from my other work. Okay. All right, so first let me show you how to change the color scheme, because I don't know why PairView chooses this kind of hot cold color scheme, but it's ugly as hell. I really don't like it. Right, and so I actually like to have the rainbow color scheme, because I'm like a colorful kind of guy. Okay. And so the way that you change the color scheme is that you're going to go to this button right here called Edit Color Map, okay? And then you're going to click on this button with the heart for Choose Preset, okay? And here you actually have a lot of different options for what color scheme that you want, okay? My personal favorite one is Jet, okay? And so let's go ahead and double click that. And then now our colors are jet colors, okay? Right? And so now I think I always felt like Jet produces a nicer kind of a visualization of what the colors look like. Yeah, it almost looks like kind of heat-seeking goggles to an extent. But for some reason, a lot of people really hate the Jet color scheme. So actually, someone actually wrote like a 20-page scientific journal paper about why the Jet color scheme is bad. And I'm like, Jesus, man. Don't you have anything better to do than to hate on a color scheme? But I personally like Jet. I think it's really nice. But Jet does have a lot of haters out there for whatever reason. Right? All right, and so that's how you change the color scheme. And so let me show you how to make the streamlines, because this is kind of another thing that's pretty cool. I'm not that petty. I'm not going to write another paper on that. Okay. All right. And so let's use this filter called the stream tracer. Okay. And let's do this one. Good. All right. And so now let's do this. Okay, and so what the stream tracer is going to do is it's going to trace out streamlines in our flow, in our flow. And so basically, what you can imagine is that we're going to put a bunch of particles in this flow, and we're going to trace their paths as they go along with the flow field. Okay, so let me go ahead and try this. Okay, all right, and so there you go. Right, and so let me go ahead and increase this length, because usually this thing is usually not enough. Go ahead and apply. Okay. All right. And so here, and so there you go. Okay. And so let me do this. Let me go back to this foam here. Okay. And let me lower the opacity of this. Okay. Just so that you can kind of see the domain in the background. Okay. All right. And so here you can see the streamlines for the velocities. And so you can see that these are kind of the paths that the velocity kind of traces out. Okay. And so it's a little bit of a different visualization than the glyphs, but I think this one kind of looks a little bit cooler too. Okay. All right. And so actually you can modify this too. And so instead of and so we can pack this with more cells. Okay. Oh. Yeah. Okay. Let's do this. And so instead of 100 streamlines, let's do 1,000. Okay. And so you can see now that it's much more tightly packed. Okay. So actually, let's go back down to 50. Actually, this is a little bit too much. Okay. All right. Let's see. What other cool things can you do in pair view? It's a lot of things. Right? A lot of things that you can do in pair view that so if I know some of you are in my 442 class, and so I know you guys have used pair view before, but these are kind of some of the other things that you can do. Okay. Can you make dank memes with it? Yeah, I mean you can make dank memes with anything, I guess. You can create the images here and write subtext for it. Okay, and so I'm kind of just stalling at this point, and so I think we're going to go ahead and call it. And so since this this is kind of our last class session together, and I know not many people are here, but since this is kind of our last time, we're all going to be together. I just want to take a moment just to say thank you guys for a great semester. So I think I speak for kind of everyone involved where would say that trying to take college during a pandemic where everything is virtual like this, like it sucks. Like this whole semester and all of last semester, like you've been in your homes, trying to do work on schoolwork, in your homes, managing all other personal stuff, like trying to interact with your classmates, trying to interact with me, virtually, and it's not easy. And it's I know it's probably one of the more difficult things you're going to do in your life. And so, I just want to say, despite all of that, I can proudly say that everyone in this class really toughed it out, and you really gave me, more effort than I could have asked. And so I just want to say I appreciate everything that you guys did. I appreciate all your hard work, and for those of you who are graduating, I just want to say congratulations, and just say what a hell of a time it is to graduate, during a pandemic and everything's virtual. So I just want to say that you guys have all my respect, all my love, right? And I'm just insanely proud of everything that you guys have done. And so even though this semester was really hard, I can say that I'm gonna miss you guys, right? I'm gonna miss the memes. I'm gonna miss all the fun times we had together, right? And you know, and I offer this for every one of my classes too. So you know, if you know, I know this class is going to end after the next couple of weeks, but you know, our relationship doesn't have to end from there. And so, you know, if there's any way that I could be a resource for you guys, if you know, if I can write you guys reference letters, or you know, if I can help you debug stuff, if you want to use OpenFOAM in kind of the next stage of your life and you want to help doing that, then you know, please don't hesitate to reach out. Like, you're always going to have my email, you know, and I'm always going to answer it, you know, as quickly as I can. And you know, I'm always going to be here for you guys, because I feel like that's what you guys, you know, that's what you guys paid for, and that's what you guys all deserve, right? Right. And so have a great, you know, rest of your evening. You know, since this is our last time, you know, I'll say, you know, well, I hope you guys all have a good summer. And then, you know, if you need help for the final project, you know, definitely keep in contact. I'm going to be here for you for that, right? And then, yeah. And so I guess for the last time, you know, Dr. Tran signing off, and I'll see you guys when I see you. Oh, my cat wants to say hi, and my fiance wants to say hi.
Angel, what
Yeah.
you were learning.
Everyone's saying hi, cat.
Do you hear her all the time during class?
Not really. She's actually
Really?
pretty well behaved. I feed her strategically, so she doesn't get loud. Yeah. I'll keep the Discord channel open for a while. So usually I close them right after the semester, but I know you guys have fun with it, and so I'll keep it open for you know, maybe until the end of 2021, or until I see that it's kind of dead. That's when I'll close it. Yeah. Oh yeah, definitely. Yeah, for sure. Thanks, guys. Thank you, everybody.